A substituent's effect on the regiochemistry and reaction rate of electrophilic aromatic substitution is not necessarily absolute. Um, for some substituents, the reaction conditions play a really significant role, like, for example, when phenol here is treated with bromine, it's going to undergo multiple brominations, even in the absence of a Lewis acid. And, um, and so we can see how three brominations occur. However, if you add acetic acid to the reaction mixture, only a single bromination occurs. These results are observed because of the nature of the substituent is affected by the pH of the solution. So this is neutral and this is acidic. Phenol itself is a weak acid. It has a pKa of around 10. And so, in the absence of acetic acid, phenol is in equilibrium with a small amount of its conjugate base. Okay, so let's look at that for a second. So here's phenol. It's in equilibrium with its conjugate base, and that's its conjugate base here. And so even though just a very little bit of this phenoxide ion, so that's called a phenoxide ion, is present, the O- substituent here is a very powerful activating group. And it's much better than OH. So it dramatically increases the rate of the electrophilic aromatic substitution. Right? And so because of that, the phenoxide anion then is the dominant reactant in the reaction. The presence of acetic acid will decrease the pH in the solution, and so the resulting increased concentration of H plus decreases the concentration of the phenoxide ion via Le Chatelier's principle. So it shifts this equilibrium this way. And so if that basically it cuts off the route where the phenoxide anion participates in the electrophilic aromatic substitution, and the only route available is the one where the electrophile reacts with the uncharged phenol, and so that's a much slower reaction that can pretty easily be stopped after a single bromination. So basically, in summary, if this is present, it's going to be super fast and we're going to brominate everything. If you put in an acid, it keeps the equilibrium here. That's a much slower rate. Only one bromination happens. Now, pH can also dramatically affect the nitration of N,N-dimethyl which is shown here. If that's treated with nitric acid and acetic acid, then the ortho and para products are mostly formed. And this is pretty much as expected since the lone pair on the substituent's nitrogen atom makes it a ortho-para director and an activator. Okay, so this is pretty much what we would think would happen. But if the nitration is carried out in sulfuric acid, and what sulfuric acid does for this is it really lowers the pH. Okay, so the pH now is much lower compared to the acetic acid here. Then that product is meta. Okay, and so the burning question in your heart, I'm sure, is, well, okay, if we lower the pH, then why does this product become meta all of a sudden? Well, sulfuric acid is so much stronger than acetic acid, it quantitatively protonates this amino group, generating the aniline ion, and that +1 charge there exists on nitrogen. So look, that's what we're showing here. Okay, so there's that plus charge on nitrogen. When you have a plus charge on this nitrogen, that's highly electron withdrawing, much like an NO2 group. So it becomes a meta director and a deactivator. And that's how we get the meta substitution there. Now, we have a similar phenomenon that can occur when a strong Lewis acid is present. For example, even though aniline, shown here, possesses a highly active NH2 group, it's really incompatible with Friedel-Crafts reactions, okay? So this is not going to undergo a Friedel-Crafts reactions. The amino group is a relatively strong Lewis base, right? So it's going to coordinate with the Lewis acid, aluminum chloride's the Lewis acid there, and that complex makes it highly deactivating and makes Friedel-Crafts reactions unfeasible. Folks, this is really super important. It's a synthetic trap that is used a lot in questions, so just kind of be aware of that. Now, when we have electrophilic aromatic substitutions that take place on di-substituted benzenes, we need to consider the effects of each of the substituents on the ring, both on their activating or deactivating abilities, as well as their ortho, para, and meta-directing capabilities. The regiochemistry of these reactions is straightforward if two substituents are in agreement, okay? And so when we say they're in agreement, it means they both favor substitution at the same positions on the ring. So if we look, for example, at p-nitroaniline, which is shown here, both substituents are in agreement, right? CH3 here is an ortho para director. The para position is already taken with NO2, so it's going to direct to the ortho position. NO2 is a meta director, so it's going to direct to the meta position, and both of those agree at the 2 and the 6, okay? Now this is completely symmetric, so if we add NO2, right, this is going to be the product that we get, which is 2,4-dinitrotoluene. And so when we have agreement like this, that works out really nicely for us, but we don't always have that agreement. So what do you do when the regiochemistry, when the groups are not in agreement? So it's a really, if we have a really helpful rule, right, would be that when these are not in agreement, so when two substituents attached to an aromatic ring disagree about where to direct the incoming electrophile, regiochemistry is usually dictated by the substituent that is the stronger activating group. Okay, that means that's the group that appears near the beginning of table 25.3. Okay, so for example, if we have M-nitrotoluene here and it undergoes a nitration, the methyl group here is going to direct the substituent substitution ortho-para to itself, right? So there's the ortho-para shown in blue. Whereas if you have the NO2, that's going to direct the substitution to meta, right, to itself, which is shown here in red. The NO2 group, when we look at this, CH3 is going to be a stronger activator than NO2. Okay, so I've written that, I didn't write it, it's written for you right here. CH3 is the stronger activating group. And so that means because it's the stronger activating group, it is going to have more influence on the incoming electrophile. Okay. Sorry if there's a pause there. I just paused it for a second, so if it broke up, that's what's going on. Okay, so like I was saying, CH3 is a stronger activating group, and so it's going to have more influence on the incoming electrophile. And so what you're going to see here is we're going to see substitution at these two places. That's where the NO2 comes in, and this is where the NO2 comes in. What you're going to notice is there's no substitution here due to steric hindrance. So okay, and so those two groups, the CH3 and the NO2, they just take up too much space for that to be a really feasible reaction. Now, maybe the burning question in your heart is, why do the more activating groups dictate the regiochemistry? Okay, that's a great question. And so if we look at the resonance contributors and the resonance hybrids, that can help us answer this question. All right, so if we broke up there, I went through and explained this all once and then didn't love it, and so I'm just going back and doing it again. I want to point out here that this top group right here, that NO2 is being added in the meta position, right? So that's being added in the meta position. And this to the CH3 as well as the NO2, right? So if the NO2 here in red, we're directing it, it would add meta. And then here in this bottom part, this is adding in the para position to the CH3, right? And remember on the previous slide, we said, look, CH3 is a stronger activator. And so it is more likely to guide the substitution, and we can look at resonance structures to see this. So if we look at the electrophile attaching in the meta position to the methyl group, right, as well as in the meta position to that nitrate group, all the resonance contributors here are going to be similar in stabilities, okay? And the positive charge is going to appear on the unsubstituted carbon. Now, when this electrophile attaches in the para position, we are going to have one resonance structure that is super, super duper stable because the positive charge is going to be on the CH3 here, and that CH3 or that R group is going to donate electron density to help stabilize it. And so this one is not very stable at all. And so what we see here is, because this one is so much more stable, that's why the para, right, is more likely to form, okay? Now, another way to kind of look at this is here, which if that broke up a little bit, I just had to pause it and restart it. So when we look at these two resonance structures, right, as really resonance hybrids, what we're going to see here is that the charge is distributed here versus the charge being distributed here, and that's where you're going to see the stabilization by CH3 here is maximized. The resonance hybrid of the uranium ion, when we substitute ortho here or here, has similar characteristics to this one, and so that's why the ortho is favored as well. So this is just kind of another way for us to look at what was on the previous slide. Now, what happens if two substituents on a benzene disagree with the placement of an incoming electrophile and have roughly the same activating or deactivating ability. And what I mean by that is they're roughly in the same location on table 25.3. And so this is the case that we see with this example where p-ethyltoluene undergoes electrophilic aromatic substitution because the two alkyl groups have about the same activating capabilities. When we look at this equation, we get a mixture of isomers produced because those two groups have nearly equal influence when it comes directing the incoming electrophile. So the answer to that is we get a mixture of isomers. Okay, and so that's just kind of something to be aware of if it disagrees. So let's do an example. Okay, so we are going to predict the major products of the following reaction. When I look at this, right, I say, ooh, first off, big thing, I have a benzene ring, right? And we really need to pay attention when we have benzene rings because of the substitution. And then the next thing I need to say is, all right, I've already got things that are attached to my benzene rings. What is going on here? Well, so I need to ask myself, is this C double bond O CH3 group an orthopara-director or a meta-director? Well, it turns out it's a meta-director. And so when we look at that, I'm going to show this here in red. Okay. And then we've got O, the M is already taken up, M and P. And so the only way or place that that's going to substitute is right there, okay? Because that's a meta-director. Then we need to ask ourselves, what about bromine? Is bromine an orthopara-director or a meta-director? And I'm going to use blue here. So here's, well, I said that real confidently. There we go. Now it's blue, right? And so there's blue for bromine. And for bromine, the ortho position is here, the meta position is here, and the para position is here. And bromine is an orthopara-director. And so what we're going to see here is it's going to favor substitution in this position, and this position right here. Okay? So now we have to ask ourselves, are the substituents in agreement? And that is not the case. And so which one is going to win? Well, bromine wins because it's nearer to the beginning of table 25.3, right? It's more activating. Right? Now, we also need to think about steric hindrance a little bit. So when we come in here and say, okay, the bromine is more activating, but this site here has a lot of steric hindrance. So it's not likely going to substitute there, and it's not going to substitute there. So it's going to substitute at the other two places. And so when we draw our products, these are the two products that we would get. I'm just going back and forth and counting my carbons, right? And so those would be the two products that we would see. Now, not all the rates of substitutions are created equally. One of the things to keep in mind is that substituent effects on the overall rate of electrophilic aromatic substitution are basically going to be additive. And so what that means is that each activating group increases the reaction rate. Right? And then each deactivating group decreases the reaction rate. Okay? And so the extent to which the rate is increased or decreased by each substituent really just depends on how strongly activating or deactivating that substituent is. And so, for example, we can see here, this is the rates of chlorination for several methylated benzenes, and each methyl group is activating. So as the number of methyl groups increases, so does this reaction rate. So for every one time that this benzene reacts, this reacts 720 million times, right? And so it's very, very activating.